Now we move into the heart of the curriculum, our technical session. The first session focuses on fundamental plasma, and I thanks Professor Ramesh Narayan for chairing this session. Please note, invited speaker will have 40 minutes, 35 plus 5 minutes, and oral talk will have 20 minutes, including questionnaire 15 plus 5 minutes. You are requested to maintain timing. After each session, a group photo will be taken. We kindly request all presenters to remain in the auditorium after their talk for the group photograph. Now over to you, sir.
Thank you. So as been stated that we have one invited speaker and 4 oral talks. It's my honor to invite Professor D.S. Patil, visiting professor, Department of Material Science, Indian Institute of Technology, Bombay. He did his master's from Nagpur University in 1976, PhD from Bombay University in 1987. And then he was a scientific officer at Baba Atomic Research Center. Started being graduate trainee in 1978-79, then scientific officer 1979 to 2014, research scientist in between at Indian Institute of Material Processing, Michigan Technological University, 1989 to 1991. And then guest scientist from 2000 to 2001 at Chemistry of Inorganic Materials, Technical University, Munich. And then he has been he is joined after superannuation in 2014, Department of Metallurgical Energy Engineering and Material Science, IIT Bombay. His expertise includes oxide ceramics, microwave sintering, thin films, plasma processing of materials, plasma chemical vapor deposition, diamond and diamond-like carbon thin films, and atmospheric pressure cold plasma devices and applications. And today, he is going to give a tutorial talk on RF and microwave-based low-pressure plasma sources. So I invite Professor Patil to come on the dais, please. 35 plus 5 minutes.
Thank you for the kind introduction, and good morning to all of you. I have been given the task of talking about the fundamentals of RF and microwave plasmas. Basically, my field is in the areas of making low-pressure plasma sources and cold plasma sources for various material processing applications. And as a part of that, now I shall be discussing with you about this, whatever little we have done in this RF and microwave low-pressure plasma sources. To start with, what is the uniqueness of these low-pressure plasmas? See, the uniqueness of the low-pressure plasma is that these plasmas are characterized by non-equilibrium nature. Their uniqueness is to generate the chemically reactive species at low temperature, because this is a medium where you have highly energetic electrons, excited neutrals, room temperature, near to room temperature ions, and this assembly of electron, ions and neutrals, it creates a situation where they generate a chemically reactive species at low temperature. And because of that, this is a state of high internal energy because of high electron temperature, free charge particles and neutrals. And due to this high internal energy, processes that are thermodynamically allowed but kinetically hindered, they proceed at very high rate under plasma conditions. The example is, if you try to deposit titanium nitride coating using atmospheric pressure CVD or even low pressure plasma CVD, then you need temperatures of the order of 1100 degrees centigrade and temperature of the reactor. No, okay. So if you want to deposit titanium nitride coatings for tribological applications, etc., with the precursors like titanium tetrachloride, ammonia, hydrogen, and all those kind of things, you need temperatures of the order of 1100 degrees centigrade. That is how it was being done in the earlier days. But if you use plasma as a medium, particularly low pressure plasmas, then at 550 degrees centigrade, you can deposit excellent quality titanium nitride coatings. And nowadays, all these titanium nitride coatings, titanium aluminum nitride coatings, etc., they are basically deposited by plasma assisted CVD. and PVD processes. And this is a classic example how the low pressure plasma medium plays a role in processing of materials. The examples for these low pressure plasmas are large area deposition of good quality coatings, diamond-like carbon coatings, cubic boron nitride coating, nanocomposites, biocompatible coatings, carbiding, nitriding of the surfaces, processing of polyesters and synthetic fibers for changing their wettability and hydrophobic to hydrophilic nature, chemical vapor deposition of exotic coatings, nanoparticle generation, chemical vapor infiltration for making metal matrix composites or ceramic matrix composites, plasma etching, sputtering, etc., and synthesis of new materials. Now, these plasma sources, particularly today we will be confining our discussion on low pressure plasma sources. They can be, these plasmas can be generated by either putting DC energy into the system, by putting some low frequency electric field, or radio frequencies like 13.56 megahertz or 27 megahertz or even higher, 80 megahertz also people have used for semiconductor processing, etc. And I shall also be discussing something about on microwave plasma generation, particularly for this laboratory uses. Now, since there are a large number of students here, I presume that all of them know about plasma generation, all these things. But just for the sake of completeness, like you have a discharge tube in which there are 2 electrodes, and these 2 electrodes, like in conducting electrodes, they are connected. They are connected by a power supply, and you have gas under the reduced pressure. Now, because of the cosmic activity or background radioactivity, there are electron ion pairs that are generated. And because there is an electric field that is existing between these 2 electrodes, these electrons are driven towards the anode, and ions are slowly moving towards the cathode because of their low mobility. And in transit, they gain energy from this applied electric field. They become energetic. They undergo collisions with the medium, and they create further ionization, and that is how we basically generate the plasma. Now, depending on how much current you are feeding into the system, the plasmas can be defined as, particularly the laboratory plasmas, the Townsend discharge, etc., they are dark discharges at very low current density. But in the normal glow, the current density is of the order of 10 to -4 ampere to 1 ampere, that region. And in the abnormal glow region, where you are using basically these plasmas for material processing applications like sputtering, CVD, etc., you should have current density of the order of 1 milliampere per centimeter square minimum, up to some tens of milliampere per centimeter square. And if you increase the current density beyond that, then basically you end up in the arc, and it has its own application field, but we are not going to discuss that. Now, again, the DC plasma that is generated, because the two species, they are moving towards the respective electrode with different mobilities, they interact with the medium, and then you have all kinds of different discharge regions that are formed in between the 2 electrode. In between the 2 electrode, basically this is the cathode, there are dark spaces, there are again cathode glow, then again there is a cathode dark space, then there is a negative glow discharge, there is Faraday dark space, and there is a long region that is a plasma column, and then anode dark space, and then the anode. Of course, we are not going to discuss too much about these things, but I just want to, for the sake of complaints, I just want to tell you that there are different regions that are formed. Now, again, this is not a very comfortable situation for making the CVD, because then if you have the dark spaces and all these things. So basically, what is done when you are using these plasmas for sputtering applications, etc., this distance between the cathode and anode, that is reduced, and that reduction is done at the cost of reduction of the positive column in the plasma. So basically, you are bringing the anode towards the cathode, and at certain distance, like you have this negative glow, and in this negative glow, because there is a space charge that is generated, so because of the space charge, there is a strong electric fields between the cathode and the space charge is on, and the ions are dragged towards the cathode with energy, and that leads to the sputtering. And basically, if you are doing this CVD, etc., using DC discharges, which is possible for conducting coatings, etc., this is again done at the cost of reduction in the positive column. Now, okay, I will skip this slide. But when you are like trying to deposit, say, dielectric coatings, the DC plasma is no good because the electrodes are going to get coated by the dielectric coating. And once they are coated with the dielectric coating, the electrode, you see, you are not able to sustain the current density into the discharge. So basically, the discharge is extinguished. Now, there are technologically demanded that you should have a process for deposition of the dielectric coating. Now, how to do that? Now, for that purpose, you have to use the RF plasmas, and this RF plasma, you have the cathode, you have the anode, or if you are using this for CVD system, then gas feed arrangement. Even chamber also can be made as another electrode, which is ground, and then this electrode is connected through the matching network and RF generator, like 13.56 megahertz generator with a associated matching network. And like, see, this generator, basically, why again this RF? Because, see, in case of dielectric, if you want to do the sputtering of the dielectric in a DC field, which is impossible, because you need the electrical supplies which nobody will be able to make. I have one slide which shows the calculation, like if you have even 1 millimeter thickness of quartz plate, and you want to do the sputtering from the quartz plate using the DC field, then you need power supply of the order of 10 to 12 volt, which nobody makes. That means by DC field, you just cannot make sputtering. However, you are at an advantageous situation because the impedance of the dielectric falls at high frequency. Now, if the impedance of the dielectric falls at high frequency, then you are better off because the RF energy will interact through the RF field, because this dielectric, whatever is put onto this cathode for sputtering application, it has lost its impedance is reduced. So RF field is able to permeate through this dielectric, and its effect can be felt by the plasma constituents. Now, how this RF plasma is generated? See, you have the RF, let us just forget at this moment that you have the dielectric. Let us assume that is a conducting electrode. Now, this conducting electrode, and it is connected to the RF generator through the matching network, and this matching network is nothing but a LC network. See, all RF generators throughout the globe, they are made with an output impedance of 50 ohms. Now, we know from the basic power transfer theorem that if you connect a load of 50 ohms across that generator, then power transfer will be maximum. So basically, the function of this matching network is to match this full load of this whole assembly as well as this LC to that of the output impedance of the RF generator, so that there is a maximum power transfer. And now, even if there is a dielectric, or let there be a dielectric or conductor, let us assume that there is an oscillating RF field, sinusoidally oscillating RF field. The frequency is fixed, that is 13.56 megahertz, or its multiple. And why it is? Because that is the frequency that is allowed for industrial applications. If you try to use any other frequency, that will interfere with the communication frequencies used by the security agencies, and you will be in deep problem. Now, once that RF field is impressed into this medium, now electrons that are generated into this medium, acid electrons that are generated by either background radioactivity or cosmic ray activity, etc., the electrons being the lighter particles, they are subjected to the oscillation. They will follow this sinusoidal field. So, like the electrons is starting from this region, it goes like this, it gains energy, then again it loses energy. So, if the electron is trying to gain energy and then losing energy, that means there is no net gain in the energy. So, as a matter of fact, if the electrons truly follow the RF lines, that means there are no collisions, then probably you will not be able to dump energy into the electron gas, and there won't be any plasma generation. Because for generation of the plasma, you need to have very highly energetic electrons. But at the operating frequencies of or operating pressures of 10 to minus 2 torr or something, where RF plasmas are basically generated, your collision frequencies are of the order of 10 to 11 per centimeter. Per second. Now, the frequency is 10 to 6, 13.56 into 10 to 6 hertz, and the collision frequency is 10 to 9 hertz. That means in one collision cycle, the electron is colliding at least 1,000 times with the other gas molecules. So whatever energy is gained, the energy is transferred to the neutral gas, and as a matter of fact, again is a two-body problem. Like when the electron is colliding with the neutral or ion, because of the difference in the mass, only a very small fraction of the energy is transferred. electron retains the energy, and as a result of that, the electron goes on becoming more energetic. That is how the electron temperature goes up. You have highly energetic electrons. And again, like when the is on the rising portion, electron will continue gaining acceleration, but in that time it has undergone so many collisions, even if it is in the falling region of the pulse. So maybe the electron have, because of the collision, it is in the favorable direction again for gaining the energy. And as a matter of fact, I will not go through the mathematics, but that mathematics, that formula is etc. is written here. So the energy gained by the electron per unit volume of the medium is proportional to the square of the electric field strength. So whether the electric field strength is positive or negative, because of this phenomena that the electron is undergoing collisions in each cycle at least 1,000 times. So electron continue gaining energy from the field and becomes energetic, and that is how in this plasma we can get energetic electrons of the order of 4 to 5 eV minimum, up to 10 eV also people have measured. Okay. Now again this because now I am successful in generating the plasma. I have the electrode, which is now, even if it is insulator, it has lost its impedance, so RF energy is able to communicate with the background gas here. And now what is happening? Now here, I will skip this discussion because we do not have sufficient time to discuss all these things, but those who are interested, I will share this PDF file with them. Okay, now what is happening? Now see, if there were two electrodes, and in these two electrodes, like there is a RF generator that is connected, then this, it is, you don't have other laser point, because this is not stable actually. Okay, so this is positive and negative, positive and negative. So what is happening, basically, or can you change that? No, chhodiye, wo nahi hoga. So basically what is happening, if you take the average DC level on these two electrodes, it will be 0. That means the electric field is going up and down across each electrode, and average the DC level on the two electrodes will be 0. That means, now, see this, this is your RF generator, and with this RF generator, like this is your LC network, and then you, through the bucking capacitor, you are connecting it to your RF electrode, the electrode that I have shown you. The function of this RF, this matching network and this LC network is to tune the reflected power. Because please remember that these RF generators, they are very expensive component. 1 kilowatt generator costs at least 15 to 20 lakhs rupees. And you have to take utmost precaution, because your whatever power is going to the load, if the impedance is not matched, that means if across the output impedance of the output terminals of the RF generator, the total impedance is not 50 ohms, that means the power will come with the reverse phase, and that will hit to the RF generator, and you are likely to spoil RF generator within no time, and it's a very big loss. So you have to make sure that the reflected power is always at the minimum, near to 0, and that is done by tuning of this. The inductor is fixed by tuning of these capacitors C1 and C2. Okay, and then there is a blocking capacitor, which through this blocking capacitor the RF energy is given to your substrate. Now see, assuming that there is a sinusoidal frequency that is going through this capacitor, the frequency being 13.56 megahertz, the impedance of the capacitor is 1 by j omega c, which is almost short for the RF frequency. Now what is happening when this plate is at a positive potential, the electrons from this plasma in the system, they are attracted onto this particular capacitor plate, and because they are attracted, the charge is accumulated here, negative charge is accumulated, and in the negative cycle, equal number of ions should come and neutralize that, but that doesn't happen because of the difference in the mobility of the electrons and ions. And as a result of that, over a few cycles or few hundreds of cycles within some second, you develop a steady state negative charge that is accumulated onto the plate onto this side of the capacitor plate. Now steady state charge will give rise to again this is electronic. See, here you have the negative charge that is accumulated, steady state negative charge, and this steady state negative charge will give rise to negative DC potential. So please remember, by incorporating that capacitor in between RF generator and your load, you have generated steady state negative potential onto that capacitor plate. And now that capacitor plate is connected to your that capacitor plate is connected to your electrode, on which either you have put your insulator or your any other substrate for deposition and all these things. That means whatever bias I have given onto this capacitor plate, that bias is being seen by the electrode, and that acquires a negative DC potential. Now what is happening? At the same time, RF is able to permeate through this capacitor, and it is felt onto this plasma constituent, so plasma is able to get sustained. There is a negative bias. Now because there is a negative bias, the negative bias will repel the electrons in the vicinity of the cathode, and you will have developed the sheath onto that electrode, and that sheath is predominantly ion rich. So under the that plasma region, now it has macroscopically it should be neutral, but it has certain positive charge, positive potential because of the diffusion of the electron. So from that positive potential to negative cathode, the ions are dragged with the energy, that is charge of the ions, into plasma potential minus bias potential, and bias potential is negative. That is plasma potential plus bias potential into charge of the ions. That is the energy of the ions that are impinging onto the cathode surface. They are transferring the momentum, so that can lead to sputtering. If you are using CVD process, they are basically impinging onto that substrate and basically helping you to get adhesion of the films, density of the films, and all those kind of things. So I have explained you about how RF sources are, basically how RF plasma is generated, what are the precautions that you have to take, and you have to always make sure that your reflected power from the RF generator is near to zero. Because if the reflected power exceeds more than 10%, see, if there are 2 kV RF voltage going, the reverse voltage is going to come as minus 2 kV, and there is going to be 4 kV peak voltage across the components of the RF generator, and you are likely to spoil your RF generator. Now, these DC potentials that is developed across the capacitor, this is bias, this is called a cell bias, and this cell bias can be measured by putting a choke in the circuit, and your conventional DC voltmeter with the grounded terminal, positive terminal grounded, so you can measure the negative DC potential. In all commercial RF generator, this arrangement is there. If it is not there, you have to make your own LC network and do the impedance matching, etc. Now, whatever I have told you, like how the potential is developed, how the bias is developed, that is given here, that is shown here. Now, what is happening? Once the bias is developed onto that cathode, so that cathode is at a steady state negative voltage, and then on that there is a superimposed RF, And with that RF, now, see, most of the time, the cathode will be negative. The calculations, I have also incorporated a slide which shows that 99% of the time the cathode is negative, or only say less than 1% of the time there is, because there is a negative DC potential on that RF is imposed now. Okay, so that negative DC potential is this one bias level. Okay, this is the bias level. Now on that, when you superimpose your RF, now most of the time it is negative, and only small fraction of the time it is positive. But it will be shown mathematically if you want to do this calculation, that more than 99% of the time the cathode is negative, and that is how you get continuous negative bias onto the substrate and associated sputtering. You see here it is shown that this is the bias, this is the bias level, and on that you have superimposed the RF. And see, earlier this was your base level, now this is shifted to this negative bias, and then because of that, most of the time your cathode is negative, and this is your base level now, the bias that is developed. Okay, now this DC bias, how it has, those who are interested in seeing like how, see, it shows only cathode is negative only for 10 to the minus 3 times of your total time pulse width. Okay. Now I will show you this. This is like we have worked on very large number of sources, RF sources, but because there is a student community, this is the one source that we developed some 20 years back in BRC, 13.56 megas, 250 watt. We were not getting RF generators from abroad, so this was an indigenously developed RF generator by electronics division, and matching network we have developed our own. And this was successfully used for making large number of diamond-like carbon coating, SiOX incorporated diamond-like carbon coating, And we have worked on so many oxide coatings and different kinds of coatings for various applications. This was one of the source. It has been used almost for deposition of 6-inch diameter diamond-like carbon, SiOx containing diamond-like carbon coating for DRDO application, for IR transparent windows and all those kind of things. So this is just to show you that, yes, RF sources are actually in running condition. Okay. This is a diamond-like carbon coating, 100 mm diameter coated stainless steel disc. Okay, sputtering I have already explained. Now I will show you one important development, that's the inductively coupled plasma. So how RF power is coupled to the plasma. I have shown you capacitively coupling. That is, you have the one electrode, you have another electrode. You put the RF generator in one electrode, the other electrode is grounded, and that is how you have coupled the power. Now there is another type of scheme where you have the dielectric tube, and on that you wrap a copper coil and you feed your RF supply to that copper coil. Now what is happening? Because see, there is a RF that is being fed into this coil. Now this RF is an oscillating field. Now this RF oscillating field will give rise to axial magnetic field, which is again oscillating at the same frequency. And because the magnetic field is oscillating, there is an induced electric field, E is equal to minus d phi by dt. So that induced electric field direction is shown by this red circle. And in this system now, if there are stray electrons that are generated by radioactivity, cosmic activity, or whatever it is, these electrons, they will be subjected to this electric field. They will gain acceleration along the direction of the electric field. They become energetic. And because they become energetic, they gain energy, they create further ionization. And this circumferential current will be flowing now in this loop. Now, this is a J, the current J is flowing in the, along these red lines, and there is an associated magnetic field. So there is a J cross B force, and this J cross B force will drag the electrons into the core. So basically, you end up in getting more density into the core, into the center, and there's less density in this region where the electrons will undergo acceleration. Now, what is happening? So this if you try to generate this inductively coupled plasma in this fashion, definitely you are going to have more density in the center, and the density will be falling. Now, see, most of the semiconductor applications nowadays, they demand very highly uniform plasma, because the technology is now 450 millimeter diameter. Okay? See, 450 millimeter diameter wafer. Now I will show you our efforts at IIT Bombay, how we have achieved 200 millimeter diameter uniform plasma. See, the scheme is something like this. You have the chamber, and on that chamber there is a dielectric window, and on that dielectric window we have put the flat spiral antenna. Like rather than wrapping the coil around the dielectric, this is a stainless steel chamber, and in this stainless steel chamber now there is a dielectric. On that we have put the flat spiral. Okay, these are the flat spiral. So basically, these spirals, they are fed by this single RF generator. There is a current that is divided in these two branches because there are two coils. And this, again, the function is same, like as the RF current is fed into these flat spiral antennas, basically, it will, the RF currents that will induce the magnetic field. Because of the changing magnetic field, there will be associated, again, that circular electric field. The species that are generated, they will be subjected to the acceleration through that electric field. They will undergo collision, they will transfer their energy, and plasma is generated. Now, what is happening actually, see, now these antennas are outside the chamber. It's not in the vacuum. They are outside the chamber. There is a dielectric plate, and as I have told you in the previous example of RF sputtering, that the RF dielectric, it loses its impedance. So basically, these dielectric plates, when they try to lose when they lose the impedance, basically the RF field will try to couple with the plasma species that are generated here, and that means RF voltages will leak into the plasma. We don't want that situation, because these sources are meant for processing semiconductor material. So you need sources with very low plasma potential. And inductively coupled plasmas have the capability to give low plasma potential. And to avoid this coupling of the power, there is a Faraday shield that is put. This is basically metallic shield, and which is grounded. In between the two quartz plate, it is the grounded shield. So if there is some coupling of the RF voltage, RF from the spiral antenna, it will be given to the ground, and your plasma that is generated is you do not have any leakage of electric field into the plasma. This is the inductively coupled plasma systems of 200 that generates plasma of 200 millimeter diameter at IIT Bombay is being used for solar cell applications and various applications. We are also using it for reactive ion etching of semiconductors and for making various devices. And this has been thoroughly characterized thanks to Professor Ramesh Narayan and his team. They have helped us in developing a Langmuir probe, RF compensated Langmuir probe. And one student was trained in his lab. Now you see the current the number density, 10 to 13, up to 10 to 13 per centimeter cube we have got. The RF plasma sources that have capacitively coupled plasmas, they give at the most 10 to 10, 10 to 9. 10 to 9 is okay, 10 to 10 also is sometimes difficult. And with different operating conditions, etc., I will show you that see the plasma density was 10 to this thing, plasma potential was less than 1 volt. Now this is the situation we want, because we do not want highly energetic, we do not want damage to the growing solar cell films or semiconductor devices. So this is one success story. This is being used for making, routinely being used now for making solar cell devices. This is the one which is being made, which is being used for amorphous silicon. Okay, this same thing. And see the uniformity. On 5-inch diameter substrate, glass substrate, amorphous silicon was deposited and its thickness were measured. Now on 5-inch diameter, you see the variation, 401, 402, 403, 400 nanometer on 5-inch diameter. 1 nanometer in 400 nanometer. It's, yeah. So this is the scenario. Of course, why we have not shown on 8-inch, because 8-inch substrate was not there. But on 5-inch, this is the uniformity. Okay, again, this is the RF CVD, because I talked so much about RF. This is the RF CVD system that we are using for boron carbide based material for depositing for thermal neutron applications. And okay, I think I have only 5 minutes, so I will be just showing you about the, now RF is 13.56 megahertz. Microwave frequency, we have done almost microwave plasma CVD work almost for 15 to 20 years. 5 PhD students, they got PhD in our lab using this microwave plasma CVD, using micro ECR sources. Now, because of lack of time, I will not be able to discuss that in detail. But micros, basically 2.45 gigahertz micros are used. Basically, they are the ones which are there in your, generated in your kitchen microwave oven. So same micro radiations are used. And these micro radiations, again, I will give the, basically, the schematic is something like that. This is micro supply. Okay. See, basically you have the micro generator, then you have the micro transmission line like circulator, cross coupler, post stub tuner, then my quartz tube, and then a sliding short circuit. The microwaves that are generated from here, they are transmitted through the waveguide. Then there is a cavity, a quartz tube in which there is a gas, and under reduced vacuum, there is a sliding shot. So microwaves, they are reflected from the sliding shot. The standing wave pattern is formed, and depending on the Q of the cavity, the electric field strength here goes up. There is a breakdown in the gas. A microwave plasma is sustained here. This is the first microwave plasma system that I made in probably 1990 or 1991, because there was no micro components available, and BRC is under bands list, so we could not get anything. So this is the one which was made from the kitchen micro magnetron, and this is the one that we have used. This has having the power of 700 watt. Then we did some work using this, but then we realized that it can generate plasma only of the order of 10 to 10 per centimeter cube. I will take some few minutes. Now, what is happening? See, earlier days, your semiconductor technology was dominated by microwave ECR sources. Now, recently, ICP has taken over because of the fact that Micro ECR sources, they are giving you good amount of uniformity and all these things, but there is a magnetic field presence there, and because of this magnetic field, there is a charge particle, damages that are associated with the growing field, and for making it too large, like 450 millimeter diameter and all these things, these inductively coupled plasma sources, the technology is now getting matured. But ECR sources of that, this one, that you, like the one at IIT Delhi, you have that multiple ECR coupled in the same plasma source and all these things that will be required. So probably that needs a huge setup, and every lab cannot afford that kind of this one. But nevertheless, this semiconductor technology, this manufacturing was dominated by ECR plasmas. Now I will show you our efforts. Now what is happening? See, these plasma that I have shown you, they were generated in the quartz tube at a pressure range of about 10⁻² torr or something. Now there is a, and that was giving you maximum density of around 10⁻10 per centimeter cube. Now you want higher density, because if higher density is there, then you can have higher deposition rates, large area and all those kind of things. So there is a scheme like, if in the chamber, if I have the magnetic, I have the magnetic coil that are surrounding this stainless steel chamber, that means there is an axial magnetic field. And then from the micro hardware, I am transmitting these microwaves through the waveguide, etc. I am getting it converted from rectangular mode, TE10 to TM01, circular symmetric mode, and that plane polarized micro irradiations, they are launched into this chamber. Now there is an axial magnetic field. So because of the background radioactivity or cosmic activity, whatever stray electrons are generated, they are subjected to this magnetic field. They are gyrating around the magnetic field lines. The microwave field, that is microelectric field, that is a plane polarized field. It can be decomposed into two components: right hand circularly polarized light and left hand circularly polarized. Now imagine the electron is gyrating around the magnetic field lines, and when the frequency of gyration of this electron, that is EB upon m, and for 2.45 gigahertz frequency, that gyration frequency can be made as 2.45 gigahertz when the magnetic field strength is 875 Gauss. So you have to tune the magnetic field strength so that it becomes 875. Now, under that condition, what will happen? The plane polarized electromagnetic wave, which is decomposed into two components, like circularly symmetric left-hand polarized wave and right-hand polarized wave. The one of them, right-hand polarized wave, will move in phase with the gyrating electron. In that process, the electron is gaining energy from the electric field. It goes on gaining the energy from the electric field. It becomes energetic. It can collide with the other species. It creates further ionization. And that is how large area micro ECR plasma can be generated. This is a facility that we set up in 1991 at at BRC, because my parent organization is BRC. And it was used, and it's still being used. Some 5-6 PhD students, they have got their PhD in diamond-like carbon, oxide ceramics, and all those kind of things, MOCVD and all these things. So these all hardware, etc., was made. And okay, this is the schematic, like how the plasma is generated, how it is diffused. And okay, this coupling scheme I will not discuss with you, because again, this 875 Gauss, how it was generated by feeding the current in two coils. And we have now ECR zone. ECR zone is the region where there is a 875 Gauss field in this one. Now when you use this system for, let us say, deposition of diamond-like carbon coating, so using gases like methane, hydrogen, and all those kind of things, the carbon species, they are going to coat the dielectric window, that is quartz, and then it will affect your micro transmission. Now you cannot remove that whole heavy things. So basically, if you shift this 875 Gauss line near to your window, then you have very highly energetic ions there, and those ions, if you have the oxygen plasma, then that oxygen plasma will clean that window, and your transmission can be restored again. So this is how we have used that scheme for. Now these are the diagnostic results. The plasma potential of 20 volt, uniform on almost 20 centimeter diameter. The zero is the center of the cylinder chamber, and 10 centimeter plus 10 minus 10. Then your electron temperature 4 to 5 eV. Of course, the power was very low. Then plasma density, if you put the error bar, it is almost uniform on 20 centimeter diameter. And this has been used for various applications. So I will not go through the applications. We have also, I'll just show one slide now. I will not show any other result, but I want to show you one result that, see, in BRC, because we could not get components from outside and all those kind of things, we were stuck up. We cannot import anything because we are in the banned list. Oh, I was very much excited to do some work on diamond CVD. Okay? So somehow my boss permitted me to set up one system. That is, we have set up one microwave plasma CVD setup for diamond deposition. We're using 2 kilowatt magnetron. And I will just show you the system that we have set up. Of course, because BRC has like objective is not to commercialize and all these things, we could not do that. But in 2013 or something, see this system was 2012 or 13, it was built. It's working fantastically well. We did a lot of work. 2-3 students, they have completed their PhD in carbon nanostructures and all these things. And this is how again, the cavity that you design, that, see, basically the plasma region which is showing, that is the focusing of the electromagnetic energy. So by adjusting the substrate holder which is conducting and your mode converter that distance, that cavity which is formed, you focus the electromagnetic energy where you have maximum electric field, and you see this is the plasma that is generated at 100 torr pressure, 50 to 100 torr pressure. It is a 2-inch tennis ball kind of a plasma in which 1.5 to almost 2 kilowatt power is dumped. Very hot plasma, not like ECR plasma which is cold, because basically pressure is high. So because of electron ion collision, the plasma is very high. And the substrates that are kept here, they are basically not, they are water cooled. Their substrate temperature is around 900 degrees centigrade. And with this, we could deposit excellent quality diamond coatings using this one. See, those black dots, etc., we were initially worried whether what it is, whether it is graphite or something. But we have seen okay, these are the diamonds on the peripheral sides. Raman shift was taken on that, and 1332 centimeter inverse diamond shift in the Raman peak is characteristics of highly crystalline diamond. And so you can see that your truly diamond, it represents truly diamond peak. And if there was a graphite, then at 1575 or 1580 centimeter inverse, you should have a very peak of very high magnitude, because Raman scattering efficiency of sp2 bonded carbon is 500 times that of sp3 bonded carbon, which is diamond. So even if there are traces, like that peak will be dominating, you will not see even the diamond peak. But it is not seen. So we have truly deposited the diamond. Then of course, this was also used later on for carbon nanostructures deposition, carbon nanotube and all those kind of things for field emission application. They are trying to utilize it for supercapacitor investigations and all those kind of things. So I think because of lack of time, I think I will stop here. And so if there are some questions, or I will, if for those who want this PDF, we'll share this PDF so that you can talk to me even later on also.
Yeah, I think, first of all, thank you, sir, for this wonderful fundamental talk and this genesis of what we are going to discuss here in the next few days. Without a plasma source, nothing is possible. So I think the very genesis of how a plasma is generated has been, sir has given us a good overview. I think we would love to hear more, but there is a constraint of the time for us also.
I want to tell only one thing. The inactively coupled plasma source that we have developed, we developed it we have been supported by BRNS and SARB in IIT Bombay. For the neutron detector project, we have set up the RI and all this. We made everything in 45 lakhs or something. There are at least 4 or 5 systems in IIT Bombay purchased from Oxford Technology. And that each system costs around 2 crore rupees. And any maintenance that is required, engineer has to come from UK or something. Here, everything can be like dismantled and reassembled. But it's not touch button. But it's working well and doing the work.
Okay.
So, yeah.
Okay, thank you, sir. And I think this session is for the students. So I'll ask the students to first have the right to ask a question. Yeah,
Yeah.
please. Mike, please then.
Thanks a lot. Hello. Yeah. Thanks a lot for the nice talk, sir. One of my question is, can we use microwave ECR source for diamond deposition?
In principle, yes, but no. Because the operating pressure in the micro ECR source is 10⁻³ to 10⁻⁵ torr. Okay? And you need basic decomposition of all these species. You know, carbon, methane, and hydrogen. 99% hydrogen, 1% methane. And this has to get decomposed into elemental carbon, carbon-containing radicals, atomic hydrogen, and all those kind of things. That decomposition will take place, but the kind of deposition that you will get is almost negligible. So my answer is, don't use it.
Okay, so
You use this because this is at high pressure, and at high pressure it goes into that. Now it is not a truly low pressure plasma. It is going to a thermal plasma. So because 100 torr is the pressure. And my suggestion is, if you want to focus on this, go for even higher pressure so that you can decompose more carbon-containing gas into these carbon-containing radicals, elemental carbons, and all these things. You have abundance of atomic hydrogen to each the sp2 bonded carbon.
yeah. So the reason for asking the first question is there is a soot formation inside the chamber.
Huh.
So are there methodologies to reduce that in terms of like to reduce the chamber
Soot formation
contamination?
is bound to be there because, see, again, this soot formation is there, but when you do this deposition, you have to make sure that certain set of radicals are there surrounding the your substrate. And soot formation will be on the chamber walls. It cannot be there on the substrate because your abundance of atomic hydrogen. Yeah. And that atomic hydrogen Hs chemically the sp2 bonded carbon.
Okay, fine.
Thank you. One more question from the audience. Anybody else from the students who want to ask? This is the right time, and unfortunately, I think Professor Patel has to leave today quickly, so you can...
No problem. They can talk to me anytime. Later on also.
So we'll share the details. Don't be shy, okay? Any question can be, no, it's not a stupid question, I can tell you that.
And in fact, this PDF can be given to everybody if they want. If anybody is interested, they can take the PDF of this.
Okay, yeah, I think we'll ask, please, the faculty side.
Temperature for?
ICP.
ICP room temperature. It is operating at 10⁻² to -3 torr. -2, -3. See, it's a non-equilibrium plasma like in tube light. But all these decompositions are taking place because you are highly energetic electrons, and that electron temperature can be up to 7 or 10 electrons, 10 electron volts. And density is very high, 10⁻13, up to 10⁻13 per centimeter cube we have measured. So basically it's a non-equilibrium plasma like any conventional plasma that is used for low pressure application. All low pressure plasmas are basically temperature is near to room temperature. You have highly energetic electrons, but ions and neutrals, they are at room temperature. And that is basically coming from the two-body collision problem. When the ion is trying to gain energy from the electric field, but it collides with the neutron, it exchanges its full momentum. Whereas the electron, when it gains energy because of lighter mass, it collides with the neutral or ion, but transmits only small fraction of the energy, retaining bulk of the energy. And that energy lost will be only in the electron mass divided by the ion mass into energy. So very small fraction is lost, remaining is retained. And that is how it goes on getting more and more energy.
As because you said that the density is almost like 10⁻13.
Yes.
And you measured it with Langmuir probes.
Yes.
So is there any other measurements which says that it is 10⁻13 in ICPs?
10⁻⁻, no, Langmuir probe is the one that we have used, and that is again repeatedly measured. And there are many reports. It's not that we are the only ones who have done, but there are internationally. And again, why 10⁻13? Because the mechanism itself is, see, you have the electric field which is circular, okay? Electrons are oscillating along these field lines. And under the J cross B field, they are pushed into the core of the plasma. Now, in capacitively coupled plasma, the electric, there is directly the RF power is interacting with that, and electrons are gaining energy. But because of their high energy, they are trying to diffuse from the plasma volume. Okay? Here, because they are getting confined. The diffusion of the electrons is minimized, and that is how you get high density there. You can do it by probably spectroscopic methods, the number density measurement, but I have not tried.
Okay. Thank you. I think sir will be here till lunch, I think.
No, I'll be yeah, I will go in another 10-15 minutes.
Okay. So any case, sir,
No,
sir
but,
is available on email, I think. So
You can talk to me anytime. You send me the mail, I'll give you all my details, and you can talk to me anytime if you have any difficulties.
Yeah. So because this session, we are interest of time, we'll have to
Yeah,
end
no
this session. One more round of applause for this wonderful talk.
Thank you.
Talk. Thank you. Thank you, sir.
I request to all oral talk presenter of this session, please upload their presentation first and then we'll start this. So I request our session chair, Professor Ramesh Narayan, to kindly present a memento of our esteemed speaker. Thank you so much, sir.
Thank you. And now we go to the next, as I said, colloquium for the students. So the students should get a chance to speak. So our first oral talk is by Deepak Rajpurohit from IPR Gandhinagar. And Deepak is going to talk, title is First Observation of Higher Harmonic Generation in Whistler Mode Excitation in Magnetized Plasma of LVPD. Deepak Rajpurohit? Not here? So Deepak, you have 15 plus 5 minutes, okay?
Hello everyone. I am presenting my talk. I am working on Whistler waves. So these are the outlines of my talks. Introduction, my device, experimental setup, major observations, summary and discussions, and reference. So first is introduction. The plasma electromagnetic wave interaction with the plasma has garnered significant attention due to its potential application in many areas like radio, telecommunications, radio wave propagation in ionosphere, and fusion plasma also. And electromagnetic waves interaction in the magnetic null, the place where magnetic field lines are cancelled out, is the which it plays significant role in the phenomenon of magnetic reconnections, which play significant role in many solar and astrophysical phenomena, and in fusion plasma also, like electron get energy and they run away. So historical background of Whistler mode waves. So in first time in 1894, Price, one operator at the telephone exchange line between Hamburg and Liverpool observed some like a rumbling sound. So he reported to his engineer Priest, and Priest further analyzed these sounds. Then he didn't understand. Usko samajh mein nahi aaya. Then he called it earth currents. These are the earth currents. Earth produce some currents. Then after 2 decades, in 1999, during the First World War, there were several detectors to detect enemy telephone communications. So one operator there, Barkhausen also detects some sound, and he relates these sounds with the ionosphere. Then after 2 decades, in 1935, Iker-Isley qualitatively described the dispersion of these waves, and he called it Whistler waves. But the quantitative dispersion relation for Whistler wave is still an open question. So after many years, Indore and his collaborator like Appleton-Hartree, Appleton-Hartree equations, he quantitatively described the dispersion of relation for Whistler, and after Second World War, it got significant attention of many scientists and various laboratories worldwide due to its potential application in many areas. And after 1960, Stengel did significant work in the area of Whistler waves. His decade-long experiment on Whistler wave enhanced our today's understanding of Whistler waves. Whistler wave and related EM waves study in LVPD. In LVPD is large volume plasma device commissioned in Institute for Plasma Research in 1998. It also working or dedicatedly working on Whistler waves related phenomena. These are the some glimpses on past research on harmonic generation in Whistler waves. In 2015, Sugawa report first observation of harmonics generation in the Whistler through the moon, near the moon using Kaguya spacecraft. There was a spacecraft namely Kaguya. उसने Kaguya spacecraft में harmonic generation है उसको report किया. Then in 2017, the professor from University of Lucknow first predicted the higher harmonic generation in the quantum magnetized plasma. Then in 1995, Birbal Singh was professor in Agra College. He detects some tweaks, higher harmonics tweaks from lightning activity in ionosphere, and he reported these are the harmonics of Whistler. Then Kranz Kino in 1965, first labs he reports some first observation of higher harmonic generation via parametric excitation in plasma. Then Jiandong Yu in Wuhan University, he also observed some higher harmonic generation phenomena from some satellite, and he did analytical work to analyze this data, and he gave a kinetic theory approach like a Vlasov-Maxwell approach. Then in 2024, Trishul Dhalia in IIT Delhi published a paper on higher harmonic generation in magnetized plasma. So these are the previous work on higher harmonic generation in Whistler waves, but the observation and verification of higher harmonic generation in Whistler waves in laboratory plasma is still a question. So in LVPD, LVPD में हमने विस्लर वेव्स का जो इंटरेक्शन होता है मैग्नेटाइज्ड प्लाज्मा में वो किस तरीके से होता है उसको स्टडी करने के लिए एक एक्सपेरिमेंट सेटअप किया। LVPD जो है 3 मीटर लंबा वेसल है, इसके अंदर हमने लूप एंटीना लगाया और हेल्महोल्ट्ज कॉइल सेटअप लगाया। हेल्महोल्ट्ज कॉइल सेटअप को हमने डिफरेंट टाइप ऑफ मैग्नेटिक सिनेरियोज को प्रोड्यूस करने के लिए लगाया ताकि हम डिफरेंट टाइप के मैग्नेटिक सिनेरियोज है और उसके अंदर वेव प्लाज्मा इंटरेक्शन है उसको हम स्टडी कर सके। सो दिस इज द अवर experimental setup. This and we are detecting wave signature and wave phenomena inside the plasma using bifailure B dot probe. They are in-house हमने खुद से बनाए हैं हमारी लैब में. And plasma characterization was done by Langmuir probes. These are the typical plasma parameter of LVPD, like discharge current of LVPD, Helmholtz charging current for producing to 20 Gauss magnetic field. This is the typical ion saturation current, and this is the our floating potential. These are the typical discharge and plasma parameter. These are the plasma parametric radial profile, means in different magnetic field scenarios, how plasma density and temperature is evolving. These are the data. The first is plasma density, plasma electron temperature, floating potential and plasma potential, and at 4 magnetic field scenarios. First there is a axial field in LVPD, BZ, and the Helmholtz field is we called BH. So first is Helmholtz is switch off, only axial field is there. Then we switch on Helmholtz in the opposite direction and equal magnitude of magnetic field. With means we are cancelling the magnetic field at the center of Helmholtz. Then minus 20 Gauss and plus 20 Gauss, and axial field is always 6.2 Gauss. This is the basic calibration of loop antenna in the vacuum and at zero magnetic field. This is the typical B dot probe से हमने जो वेव को डिटेक्ट किया था. अवर बी डॉट प्रोब इज 3 एक्सिस बी डॉट प्रोब. तो वो बी डॉट प्रोब है वो एक ही पोजीशन पर एक्स वाई एंड जेड जो मैग्नेटिक फील्ड के कंपोनेंट है तीनों को एक साथ मेजर करता है. सो दिस आर द मेजरमेंट. दिस इज द फर्स्ट प्लॉट इज द करंट पल्स ऑफ लूप एंटीना, एंड दिस आर द बी एक्स बी वाई बी जेड, एंड दिस इज द FFT, Fourier fast Fourier transform, and we can see there are harmonics peaks and at some positions, some certain frequencies. This is the Helmholtz coil field measurement. this is the magnetic field using magnetic field configuration using MATLAB, 2D MATLAB code. And this is the loop excitation of plasma with Bz is equal to 6.2 Gauss and Helmholtz magnetic field is 20 Gauss. So these are the typical contour plot. And in this plot we are getting our harmonic structure, means when we switch on Helmholtz magnetic field toward the axial field. So when it's superposed with our axial magnetic field, then frequency of loop exciter is shifted toward the higher harmonics. Means we are launching wave with loop exciter, and this wave further interact with plasma and excited these harmonics. You can see harmonics peaks at 350 kilohertz, 450 kilohertz, 600 kilohertz, and our typical loop exciter का जो fundamental frequency है वो 150 kilohertz है. So this is the clear indication of harmonic generation in the Whistler mode excitation in the LVPD, magnetized plasma of LVPD. And this is the magnetic field profile with minus 20 Gauss of Helmholtz, means we are opposing the magnetic field of Helmholtz with the axial magnetic field. So in vacuum, and when we switch the direction of Helmholtz magnetic field, then our whole structure is shifted toward the radius of Helmholtz field. मतलब जब हम मैग्नेटिक फील्ड को उसकी डायरेक्शन में लगाते तब हमको हार्मोनिक्स मिलती है, और जब हमको हेल्महोल्ट्ज मैग्नेटिक फील्ड की डायरेक्शन को हम ऑपोजिट कर देते हैं, तो पूरा जो वेव स्ट्रक्चर है वेव मैग्नेटिक फील्ड का वो हेल्महोल्ट्ज की रेडियस के बाहर शिफ्ट हो जाता है. सो दीज आर द टिपिकल काउंटर प्लॉट्स. Then we create the magnetic null at the center of Helmholtz coil with producing 6.2 Gauss in both LVPD axial field and Helmholtz magnetic field. This is the MATLAB plot. And this is the magnetic null configuration of Helmholtz coil in plasma medium. Means in this scenario, plasma is there and field cancellation is there at the center of LVPD. So these are the typical structure. In BX and BY component, whole structure is shifted outside the radius of Helmholtz coil. But in Z component, there is also some wave profile and finite wave magnetic field at the center of Helmholtz coil or center of LVPD, because loop exciter, Helmholtz coil and center of LVPD or are collinear at a common center, common axis. So these are the summary and discussion. So in our experiment, first we report wave polarization, because in the absence of plasma, only BX component and BZ component is there. But when we switch the plasma, then wave interact with the plasma and wave polarization comes into the picture, and probably it is the right-handed circularly polarized wave, because Whistler is RHCP waves. So our first finding is wave polarization in laboratory plasma. Second finding is we are getting higher harmonics of Whistler mode excitation, and it is the first kind of its laboratory observation. As my knowledge, no one reported this work in laboratory previously in Whistler mode. In laser plasma, there were many papers on higher harmonics, but and electron plasma wave also, Professor Cow and Professor Soda also did seminal work on higher harmonic generation in Whistler plasma waves, ion acoustic waves. But Whistler modes पर भी theoretical काम हुआ है, but experiment में this is the first observation as per my knowledge. If something is there, I don't know. I didn't see in references on literatures. And the third thing is, when we create the magnetic null at the center of Helmholtz coil, in this scenario, whole wave structure is shifted outside the Helmholtz coil. Means पूरा जो wave profile है वो shift हो जाता है, और Helmholtz जहाँ पर magnetic null बन रहा है वहाँ पर हमको कोई भी वेव मैग्नेटिक फील्ड और स्टैटिक मैग्नेटिक फील्ड कुछ भी नहीं मिलता है. स्टैटिक मैग्नेटिक फील्ड इज जीरो एज अवर एक्सपेरिमेंट, एंड वी आर डिटेक्टिंग वेव मैग्नेटिक फील्ड विद यूजिंग by failure 3-axis magnet probe. So it is also zero. So magnetic null is the key thing in the magnetic reconnection. So further our plan is to do more experiment on magnetic nulls with more than higher magnetic field, because in LVPD we can go up to 100 Gauss of static magnetic field. Now we are using only 6.2 Gauss, and in pulsed mode, we can go up to 1 kilo Gauss also. This is the calibration of our magnetic probe in our laboratory, means which magnetic probe we are using for our experiment. It is fully calibrated, and its electrostatic pickup or any electrostatic capacity pickup is negligible in our knowledge. And we are using a optimized design for B dot probe as per suggested by P.H. Lowenhort. P.H. Lowenhort in his paper of 1993 RSI paper give a design to reject and to mitigate inherently electrostatic pickup, so that we can only electromagnetic signal, and we are interesting only in electromagnetic signal. This is the set of our loop exciter. Loop exciter का power supply है PFN, pulse forming network based thyratron based power supply है. इससे हम loop एंटीना को चार्ज करते हैं.
Questions from the audience? Yeah, I think there's two hands raised. So,
My question is, how do you know it is Whistler wave? I mean, what are the signature from which you can say the Whistler wave?
First signature is frequency domain. Means I didn't mention in these slides, but the frequency range of Whistler wave is between the electron cyclotron frequency and ion cyclotron frequency, and what frequency we are getting is the in between electron cyclotron frequency and ion cyclotron frequency of our device, large volume plasma device.
Do you measure the wave propagation direction? Wave propagation direction.
Wave propagation? Means till now we didn't measure the wave propagation direction, means K perpendicular or K parallel, but this is the propagating in the axial direction of LVPD only.
Okay.
How you quantify the frequency as a harmonics? Matlab you tell na this is the higher harmonic generation. Then how you quantify a harmonics?
Means if we are putting a pump wave inside the plasma, this is the frequency of this wave is our fundamental frequency, and we are inputting the 150 kilohertz of electromagnetic signal inside the plasma using our loop exciter, and the key feature and we are getting 350 kilohertz, 450 kilohertz. 450 kilohertz is the third harmonics of 150 kilohertz, and 600 kilohertz also, and these are the clear peaks on harmonics. And the key feature of our experiment is that unlike the laser plasma interaction में हमको एक distinct peak मिलती है, but हम एक फंडामेंटल फ्रीक्वेंसी जो जा रही है वो पूरे एक ब्रॉडबैंड में जा रही है, मींस 150 किलोहर्ट्ज तो है ही, उसके आसपास की भी फ्रीक्वेंसी है, तो हमको हार्मोनिक्स में उन फ्रीक्वेंसीज के भी जो हार्मोनिक्स है, हायर हार्मोनिक्स, वो हमको मिल रहे हैं.
Apart from frequency doubling or tripling, is there any other way to say that a frequency is a harmonics of the fundamental frequency?
Yeah, for we are planning.
Did you measure some mode number of the particular frequencies, so that mode number also should be double if one frequency is a harmonics of a fundamental frequency?
No, till now we didn't do, but we develop a analytical model to means matching our result with the theoretical and analytical predictions. Kinetic model and dielectric approach, वो उसका जो analytical framework है वो हमने अभी तक रेडी कर लिया, बट उसके अंदर सिमुलेशन और न्यूमेरिकल मेथड से हम प्लॉट्स जो है वो मैच करेंगे फ्यूचर.
ठीक.
I think there's one more question.
Deepak, why only Whistler wave is right circularly polarized? I need to know. Why Whistler wave we observe na Whistler wave only right circularly polarized? Any comment on that?
बिकॉज टिल नाउ मतलब अभी तक विस्लर वेव का जो डिस्पर्सन रिलेशन है वो हम जब फाइंड करते हैं वो कोल्ड प्लाज्मा थ्योरी से आता है, जो स्टोरेन है 1950s में दिया था। तो कोल्ड प्लाज्मा थ्योरी से हम डाइलेक्ट्रिक टेंसर निकालते हैं, वहाँ से डिस्पर्शन रिलेशन फाइंड करते हैं। तो वहाँ पर जो विस्लर का डिस्पर्शन रिलेशन है CMA डायग्राम में, वो विस्लर का जो डिस्पर्शन है वो पर्टिकुलर राइट हैंड सर्कुलरली पोलराइज्ड वेव के डोमेन में ही आता है, सो दैट वी कैन से इट इज राइट हैंडेड सर्कुलरली पोलराइज्ड वेव, एंड इन सम केसेस इट इज ऑब्लिकली आल्सो मींस।
Yeah, there's one more question in front.
I have a question. So you have shown Whistler mode, okay? So what is the operating frequency here? Frequency, excitation frequency.
Between the 150 and 200 kilohertz.
No, your plasma generation, RF excitation.
No, we are using filamentary source, DC plasma.
DC plasma?
Yeah.
Okay,
we are
okay.
using DC filamentary source, which consists of 162 tungsten filaments, and it is also it's kind of largest filamentary source.
Okay.
Thank you, sir.
Okay, I think due to short of time, we will end the discussion here. One round of applause for Deepak Purohit. Thank you. So our next speaker is also from IPR Gandhinagar, Ardendu Shekhar Mishra. And Ardendu is going to talk on relativistic, cylindrical, and spherical plasma waves. Over to you, Mr. Ardendu.
Hello, good afternoon, everyone. Myself, Ardendu Shekhar Mishra. I am a second year research scholar from IPR. So before starting this presentation, I would like to first thank the PSSI committee members for giving me this opportunity to present my ongoing research work. So with that note, so please allow me to start. So the topic of my presentation goes by relativistic, spherical, and cylindrical plasma waves. So these are my contents. So first I will be talking about the problem, then the mathematical formalisms of the problem, then after doing all the mathematical formalisms, what I am getting, like the wave breaking and phase mixing phenomena, and various insights about the phase mixing, like it's like the phase mixing time, and I will be giving some proofs or like simulation proofs to verify the analytical results. And then I will be talking about something called turnaround time, and all these 4 or 5 things. It's for spherical oscillations. Then for cylindrical oscillation, I will be talking the same things, and then I will conclude the talk. Okay. So before starting that, I want to starting the talk, I want to talk about the problem, what the problem really is. So first we are considering cold plasma, where the ions and electrons are sitting, or the electrons are sitting on the top of the ion. Then we will be giving a push or a perturbation to the ion, and we will be giving a push to the electron, and then we will study the motion of the electron. So this is a video that represents my problem. So the blue dots are the ions, and the oscillating tiny dots, they are actually electrons. So at time 0, as you can see, at time 0, before giving any perturbation, the ions and the electrons, they are at the same place. Then I give a perturbation. That means I give a push to the electrons. So the nature of the push is spherical. That means that I am giving the perturbation whose wavefront is a spherical wavefront. That's why the electrons are going spherically outward from the ion. Then because the electrons and ions are separated, now the Coulomb's force comes into the picture, and that makes the electron oscillate about the ion. So to describe this phenomena, so I am taking help of the fluid equations, like continuity equation, momentum equation, and obviously Maxwell's equation. Then as the momentum equation is, nonlinear, we cannot actually solve it in law frame. So that's why we are taking the help of a transformation. And this transformation is generally called Lagrange transformation. So what do we do in the transformation that, like from lab frame, we go to a different frame called fluid frame. So, so these are the transformation equations written in the red color. And here the time remains same, that is the time of observation in lab frame and in fluid frame, that remains same. So using this transformation, I rewrote the equations, the continuity equation, the momentum equation, and the Maxwell's equation. Those are given in the right side of the screen, that is mainly in blue color. So the first equation, in the blue color given, it's the density of a fluid element in the lab frame. Okay, so solving the rest of the three equations, I can get the electric field, and the electric field here it's dependent upon the the equilibrium position R0 and the push we are giving to the electrons, that is defined by capital R. Then using Maxwell's equation, then using Newton's equation, we can get the equation of motion of the electron sheet. The electron sheet means the electrons on the circumference of a particular radius. I am calling that as a sheet, and that sheet actually oscillates about the ion. So the equation written below represents the motion of the electrons there. Then we need to solve this equation. It is very evident that this equation is a non-linear simple harmonic oscillator equation. If R was 0, okay, if R was very small compared to R0, then if we solve this, we will get a simple harmonic oscillator equation. So as there are many terms, so that makes the equation non-linear, like the 1 plus R0 divided by C square. This comes because of the relativistic part of the equation. Okay. Then we solve that equation by doing some transformation, or it's not a transformation, like we solve that equation using Lindstedt-Poincare technique to get the frequency with which the electron sheet oscillates. So we found that the equation, we found that the omega, what is it called? Frequency, okay, the omega, it depends upon the equilibrium position R0. So, like I have mentioned here, two things. One is geometrical effect and the relativistic effect. The geometrical effect represents the spherical wavefront, and the relativistic takes account into the relativistic mass of the electron. So even if the relativistic is not considered, still the frequency depends upon the equilibrium position. So because of the spatial dependence of the frequency, we see a very peculiar phenomena. Okay, so to describe that phenomena, I have given two examples. Like if the frequency depends upon space, like what happens, and what happens if the frequency is independent of space. So so if the frequency is space independent, then the oscillator or the sheet will indefinitely oscillate without crossing each other. But if the frequency depends upon the space, okay, if the frequency depends upon the space, then a time comes where the electron sheet will cross each other, and that phenomena we call phase mixing. And once they start hitting each other, the wave cannot sustain. So that point we call the wave or the oscillation breaks. Now in this slide, I will be talking about the phase mixing time or the wave breaking time. So for that, we are giving a perturbation, and the perturbation is given in terms of Bessel function. Because we choose Bessel functions because the Bessel function is the because the Bessel function is the basic set for the spherical symmetry systems. And to see oscillation, we need to put the electric field at the center as well as at the boundary of the like system 0. So with keeping all these things in mind, we give the perturbation in terms of Bessel function of first order. So then we using this equation in the frequency formula, we for the condition delta less than 1 and for very small perturbation, we calculated the frequency. And we take a reference from Dawson's theory, like what he says that the phase mixing time is inversely dependent and inversely proportional to the rate of change of frequency, spatial rate of change of frequency. So from that we found that the phase mixing time actually depends upon the inversely proportional to cube of the amplitude of the perturbation. Then to make sure that this actually occurs, we did a simulation, and through that we verified that the phase mixing time actually depends upon the cube of the, or the inverse of the cube of the amplitude. So then we go to calculate the turnaround time. So like for that, we need to excite a wave for the system. So what do we do actually? So we like the solution of the equation of motion here. The solution of the equation of motion, we consider it is a outward propagating wave that is given by the iconal function psi. Then from that we calculate the calculate k, the wave vector, and the frequency of the wave. Then using using that k and omega, we calculate the relationship between k and the rate at which the frequency changes. So what actually we did then, like if the wave is propagating, like outward propagating, then initially k will have some positive values, and if it is coming back to the center, then it will have negative values. So in between them, the k must have passed through 0. So taking this condition, we calculated the turnaround time of the wave. So the turnaround time, like as we found here, is also inversely proportional to the rate of change, the spatial rate of change of the frequency. Then we calculated the wave breaking time for the same, and the wave breaking time, to calculate the wave breaking time, we take a condition, like at the point of wave breaking, the density goes to infinity, because as you can see here, like if 1 plus del r by del r naught goes to 0, then the density will go to infinity. So at that point we call the wave breaks. So using this condition, we calculated the wave breaking time, and it also comes it is also proportional to the it is also inversely proportional to the rate of change of frequency. Then we did the same for the cylindrical case also, and here also the phase mixing time is inversely proportional to the cube of the perturbation amplitude. Okay, so to conclude the talk, so I would like the cylindrical and spherical oscillation will always break for any arbitrary perturbation. So no matter what is the amplitude of the perturbation, like a time will come where the wave will break, and this is independent of the choice of initial condition. Here I have given the initial condition in terms of Bessel function. We can give any arbitrary function, but still the scaling law will be valid, and all this theory is valid if there is only radial symmetry. Okay, so thank you.
Okay, thank you. Questions from the audience?
Yeah, can you hear me? Yes. So, in your expression for omega, you, I think, gave that it is corrected by a relativistic term and some another term. Geometrical. So, why do you call the last term as a relativistic effect? Means, I didn't see any relativistic argument. It's just electromagnetic scenario. So,
No, it's not electromagnetic. It's electrostatic.
Yeah, so why you call it a relativistic effect? I
Because
do not.
because we often like, okay, so to answer this question, so let's go to the equation of motion of the electron sheet. So there you can see the relativistic effect, like 1 plus r naught by c square.
Okay.
And if you ask me where that come from, like we get that from the relativistic Newton's law.
Means that can come also from like retarded effects
No,
in
it's not retarded.
electromagnetism.
There is no, this is not an electromagnetic wave. It's a electrostatic
Okay.
wave.
Okay. Yeah. Thank you.
Any more questions? So I've been instructed, yeah, just one question more because we are running this short of time. So
About the wave or an oscillation first? Means like in general case we move a plasma oscillation. Right. So that is an oscillation only. So there is no wave in there. So if we consider here your picture is shown, that is more or less like an oscillation. Means it. So in that case, what will happen to those oscillation if we take a spherical case or a cylindrical case?
Sorry, sir, like I didn't get your question. Could you please repeat?
Like in a cold plasma, if I perturb electron sheet, I will get an electron oscillation, right? So until that it is only an oscillation, no waves.
Okay.
Okay, so if I do that here in your case, so because you have a certain geometry of ions and then you have certain geometry of electrons and then you have mean position and they are oscillating.
Yes.
So it's an oscillation only, right?
Yes, it's still an oscillation. But
So in this case only, I am not putting a wave perturbation or anything else.
So like if you are not giving any perturbation, then how could we?
No, I am given a perturbation, then only this oscillation starts. So in this case, it converts into wave or it remains an oscillation? And what happens to that oscillation if I take this kind of spatial geometry?
Okay, like even if you take the oscillation, it will still break. So oscillation breaks means that the density of the electrons like will go to infinity at some point.
thank you. A round of applause. Okay, so we need to our next speaker. Our next speaker is Ms. Libin Varghese. Mr. Libin Varghese from Gandhinagar, but DIIST. Right, please.
Good afternoon, everyone, and thank you for giving me this opportunity. Today I'll be talking about parallelization and scalability studies of 2D 3V electrostatic peak MCC code for E cross B low temperature plasmas. So the outline of the talk will be, first I will be giving the motivation, why we are doing this, then a little bit introduction into the low temperature plasma, then the parametric studies of an E cross B low temperature plasma using 2D simulations and why we need to like do the parametric studies and all. And then the anomalous electron transport, what it is, how it, the origin of anomalous electron transport and its effects. And then since we are doing this in a simulation, there is a computational thing that is called scaling factor and its effect on the plasma transport. Then we look into the benchmark code and parallelization and scalability studies of it. So the application for E cross B based low temperature plasma, here I have put two pictures. One is of Hall thruster and the other is the Robin setup, which is a negative ion source in IPR. So basically you have an, if you see this, the diagram that I'm showing here on the right hand side, it is showing the basic properties. You have a plasma flow and you have a magnetic field applied, which is perpendicular to the plasma flow. This in effect creates an E cross B effect and creates some few instabilities and all, which is what our motivation is and what are the effects of these instabilities. So for giving the flavor of the landscape which we are working on, you can see what are the operating pressures. It's just few millitorr. You have very low plasma density, that is 10 raised to 16 to 18. Your ion temperatures are at room temperature. Your electron temperatures are at 1 to 10 EVs. The max magnetic field we use is 1 to 10. So this is in general, general case for an E cross B plasma. We'll pick any one of them. This is the scenario for any E cross B system. Low temperature plasma system. So the before going to the governing equations, we can see what this low temperature plasma is. Here I have shown a picture of a very weakly ionized low temperature plasma. You can see it's a collection of electron ions and neutral gases. The temperatures of electron are very high. It can go up to 10 EVs or more, but the ion temperatures are at typically room temperatures. And that is what creates the unique interaction between these different thermal energies of constituent particles. So the governing equation, this particular equation, the Boltzmann equation, using this we can track the phase space evolution of the plasmas in time. Here I have, from this we can derive what is the momentum conservation equation. Particularly if you look into the right hand side and left hand side, I am equating what are the force densities and how it is different kinds of force densities and how it affects the evolution of plasma. So there is a collision term which we can look into the collision term. Classical theory says that since these particles will collide them with each other, and it will have in turn an effect of plasma transport. So if you break that down into, since we are going to do a 2D simulations, we can break that down into its vector forms, and we can find out which term is affecting the plasma transport in which directions. So there is a collision term which is the collision force density that is shown here, and then you have an electron ion friction force, which is actually as you see the vector form, this is in the y direction, which is actually going to affect the plasma transport in the x direction, which is in the direction in which the plasma actually flows. So classical theory says this is the mobility of electrons that you get when you incorporate these collision, that is in presence of a magnetic field. This is what the classical collision is. But experimentally, when we verify this phenomenon, we see that there is an extra collision, and we want to account for where this anomalous electron transport comes from in case of E cross B plasmas. So for that, we will be performing a parametric study on the E cross B low temperature plasma using a simple 2D simulation case. I have picked here, this is my domain here, if you can see. This is the source term from where we are generating the plasma, and this is the magnetic filter which is perpendicular to the perpendicular to the plasma flow, and then we have a bias voltage to create an subsequent electric field in this simulation. Then we have the periodic boundary conditions applied on y direction. So in essence, the losses will occur from only the x directions. You have 0 volt bias on this side and positive bias on this side, in effect creating a plasma flow. So if you look at the typical plasma parameters, these are the plasma parameters. We will be changing the bias voltages, and we will be changing the magnetic field, the magnitude of the magnetic field, and see how these, what kind of effects this has on the plasma flow. So why do we need to do this kind of simulation using particle in cell only? The question is, this can be done through fluid simulations also to actually, but particle in cell very accurately tracks the particles in phase space, and this anomalous transport has been known in like in literature that it is due to the instabilities, and which cannot be directly modeled through simplified fluid models because of the assumption that the underlying electron velocity distributions will be Maxwellian, which may or may not be the case, and particle in cell can effectively track that. So why the parametric studies? Because in real world scenarios, you can have multiple configurations, you can have different electric fields, different magnetic fields, and we just want to quantify the effects of these on the plasma transport. And the instabilities, it is known that it is the primary mode which enhances the electron transport in E cross B discharges, and that is what we want to look at. So I have shown pictorially here a video which I have generated from my own simulations. This is based on zero magnetic field and a bias voltage of 20 volt. We have the source term which creates the plasma, and it is flowing across the domain. So what happens, and I have shown it in terms of time also, like you can see the evolution in time. What happens when we introduce the magnetic filter here? You can see that as soon as magnetic filter is imposed on this kind of a flow, you can see the instabilities being developed. These kind of instabilities is what we are going to look like, why these instabilities occur and what are the effects of these instabilities. So typically particle in cell time loop looks like this. You have the computational view on the left hand side top, and you have the time loop on this side. There are multiple solvers involved in a particle in cell code. You have the charge deposition subroutine to actually deposit the charges from the particles onto the grid points on the structured Euler grids, whereas the particles are on the Lagrangian grid, which are free in space. It can move. You find out what is the potential on the grid, then you find out what is the electric field on the grid, and from that you update the velocities of the particle in mover subroutine. So from our studies, what are the observations from our studies? Here you can see we have modifying the biased potential, and we have applied a zero magnetic field. In that case, you can see as the potential is being increased, the plasma potential is also increasing. But this is not the case. It doesn't happen infinitely. That means you apply infinite potential, the plasma potential keeps rising. There is a saturation point where the plasma potential will match the amount of applied potential. The average electron density and the average electron energies is shown on this side. So what happens when you apply a magnetic field of 7 millitesla? You see that if you see for a 0 volt bias, you have a sudden drop in the potential. But what happens to the other two cases where you have a positive bias of 10 volt and 20 volt? You see that the gradient, now they both are lying almost on top of each other. And now the gradient of the potential will reduce, which in effect will reduce the plasma transport across the magnetic filter, and that effect is seen here. So you can see that the increase in the plasma, increase in the electron density for the specific case of 20 volt, where the gradient is perfectly matched, and now the electrons are completely trapped inside the magnetic filter, and they start oscillating there. When you trap the electrons in the magnetic filter, you suddenly have a drop of electron energy, which is shown here. Now, what is the effect of these on the plasma transport or the electron transport? Here I have shown the momentum conservation equation. We will be focusing on that term, which is REI, which is the electron ion friction force, or force density, which is calculated from the simulation using this particular equation number 4. So here you can see I have calculated what is the average E cross B. It is averaged in the E cross B direction, that is in the Y direction. If I can just use the point. Okay, so this it is averaged in this direction, and we are looking at the spatial, looking in this X direction, how it is changing in the X direction. So you can see near the magnetic filter, that is the peak of the magnetic filter. If you see, this is the peak of the magnetic filter. We have a peak in in this particular term, that is REI, which is the electron ion friction force. It is actually assuming that you have an electron which responds very quickly to the applied electric field, magnetic field, but the ions are slow to move. And in effect, this motion of two different velocities will create a friction among them, which is actually seen here. So you can see I have plotted the magnitude as well, which is shown pictorially in here. Now, what is the effect of this particular electron ion friction force? Here I have plotted the electron fluxes, which is again averaged in the E cross B direction, and it is plotted in the spatial variation in the X direction, that is in the flow of in the direction of plasma flow. And you can see that without the magnetic field, it is evenly distributed about 0. But as soon as we apply a magnetic filter, the effect is seen clearly here, that the more amount of flux is now coming towards the left-hand side electrode, which is the effect, which is the anomalous electron transport. Here I have shown the pictorial representation of the ion flux, which is what we want in a typical E cross B system. That is, we want to collect the ions on the right-hand side, and the velocities must be high. And the flux must be high in case of Hall thruster, or in case of a negative ion source. That is what our end goal is. So the effect of scale factor in a particle in cell simulation. So why do we use the scale factor? First of all, it's a standard technique that is used to reduce the computational load. So what are we doing? We are simulating at lower densities, and are assuming that at lower densities we'll get the instabilities which are seen in the lower densities will scale linearly. That is what the assumption is. But so now we can look into the numerical constraints for a particle in cell code. You can see delta x must be less than the lambda d, and delta t must be less than 0.2 by omega b, which is a CFL condition. And 71, if we are assuming 71 particles per cell, For this kind of a simulation domain, I have taken, this is a 24 centimeter cross 10 centimeter simulation domain, and if we use the scale factor of 1, that is the real density, we require 17 billion particles as well as 20 million iteration to complete a 20 microsecond simulation, which is computationally very heavy, even in terms of modern supercomputers. So we use a typical scale factor in order of thousands, which is 20,000. That is, we have reduced the scale of the simulation by this amount. And you can see that now we are dealing with only millions of particles and a million iteration. That way, we can reduce the computational load. But what is the effect of these kind of scaling? That is what the real question is. So when we look at the force density calculations, you can see that with the scale factor, we have a significant reduction in the force density, and this in effect will lead to a very estimation of the subestimation of the electron flux. So we need to do it without scaling. So without scaling, this is the 2D benchmarking code which people have performed without scaling. As you can see, this particular simulation domain is picked from the configuration of Hall thrusters, and it's only a 2.5 centimeter cross 1.28 centimeter simulation domain with simulation domain. Why this kind of simulation was performed? Because we needed to first establish the fact that the scaling factor cannot be used, and we need simulations with real densities. 7 international groups came together to verify the accuracy of their code by looking into the physical parameters and everything. So we performed this particular simulation, and this is what we get. So I'm running short of time, so I'll just show what is the effect of this benchmark code. It requires around 40 million particles, and on an average, these 7 international groups required 60,000 core hours, and this is where we stand. From our in-house parallel PKMCC code, we got around 46,000 core hours, which is comparable to LPP France and TAMO USA. But you can see Laplace and Triple PL, that is the Princeton Plasma Group, they have a pretty good code. So this is the standard technique which people use for particle and cell code for parallelizing, that is using multiple grids for cores. So you have n number of cores, you need n number of grids for charge deposition, which typically slows down the simulation. So that is the effect here, which I am showing, that the scalability is very low for the conventional method, that you are increasing the number of cores, but yet you are not getting any speed up. That is that is the conventional method. So we developed a particle thread binding charge deposition scheme, which requires only 4 private grids as opposed to n number of private grids, regardless of the number of cores. So now you can use infinite number of cores in theory, and the effect is shown here. We have removed the scalability issues, and we have tested it on a distributed system with thousands of cores, and in effect we can see up to 5 times increment. You should look at the blue curve, 5 times speed up. So in effect, we have brought down that time from 46,000 to 9,200, which is comparable to some of the best codes available right now. So for more information, you can go to this archive paper that we have published. So in conclusion, I'll say that electron-ion friction force densities arises in the presence of magnetic field, and it strongly influences the electron transport across the magnetic filter. Then we looked into the effect of scaling and its effect on the electron-ion friction force, why parallelization is important, and I have shown results from my own in-house PKMCC code where we have verified, benchmarked it against the several international groups. We have a very good scalable and accurate code. And for more information regarding the verification of low temperature plasma electrostatic codes, you can go to poster number 6, where Ayushi will be presenting results from our own code. Thank you.
So, questions from the audience? I have 2 questions. First is that are the ions and electrons both magnetized in your system?
No, only the electrons are magnetized in this system. We are using a very low magnetic field here. The ions are unmagnetized relative to the scale of the system.
So how you put that in, means the electron, so how much, what is the ratio of this electron gyro radius to your system size?
So if I have Let me see if I have the parameters here. You can see the Larmor radius for the ions as well as the Larmor radius for the electrons. And you can see the cyclotron frequencies as well. So in this case, the electrons are magnetized, but the ions are not relative.
Okay, and the second question is that you have considered this viscosity, but what about the polarization current in that?
We haven't looked into that. This is an electrostatic peak code. We haven't looked into the polarizations of particularly which direction the electrons are gyrating. Yeah.
No, but are there no ambipolar fields that get generated?
Yeah, they can be generated.
Will that also not have an effect on this?
It may have an effect, but this is a particle in cell code, and it will automatically get reflected in the results. Yeah.
So was that presented? I missed it.
No, we didn't present any ambipolar effects here. Yeah.
So I just asked him the question whether ambipolar fields were present. Yes.
Yeah.
I'll answer the question. Anybody else in the audience? Yeah. I see the students are lunch आ गया है पास में तो भूख लग रहा है शायद.
Very good talk, by the way. Your debye length is very small. You said,
Yes.
How many particles do you have in a debye length?
I'm not really sure. I didn't look into that. I think around 70. It starts from, I think it starts from 75 and goes up to 400. I think, if I'm not wrong.
So not a very large number, because so you have to do the scalability with the number of particles.
Yes.
Because here the statistical error can be high
Yes,
with
the
the low number of particles in the.
Yeah, so this particular benchmark simulation, here they have varied that number, and with the different particle densities to verify what is the minimum amount of particles that you require to get statistical accuracy and where the convergence lies. So it has found that with starting with a 75 ppc, you are more or less at a good compromise between computational load as well as the statistical accuracy.
Good, thank you.
Interest of time, we'll end the talk here. We give one more round of applause for Libin. Thank you. So our next speaker is Harihar Pradhan from IIT Hyderabad. Thank you.
Hello all, I am Harihar from IIT Hyderabad. I work with Kiritan Bhatt, and yeah, I would like to thank for giving me opportunity to discuss about my work. So today I'll be discussing about scaling behavior and energy conversion, the processes that take place during relativistic magnetic reconnection. So this is the content that I'm going to cover. Now first we'll look into a Sweet-Parker reconnection model, which helps in studying reconnection in resistive MHD. Then we'll look into the energy conversion processes that happens during reconnection. We'll also look into the inflow and outflow dynamics of the flow in the plasma by doing a sigma scaling. Sigma is the magnetization parameter. Then at the end, we'll look into the energy partition, like where the energy goes in like thermal energy, kinetic energy, and magnetic energy. So at first, in ideal MHD, the magnetic field lines are frozen to the plasma. So wherever the field lines go, the plasma moves along with it. And wherever the plasma goes, the magnetic field lines goes along with it. For reconnection to happen, this field line must cross each other. They must break and reconnect. So how does this happen? Now, here, if you see, if you have antiparallel magnetic field lines and they're present very close to each other, you will find a thin current sheet forms. This purple one. So in this region, even if a small amount of resistivity is present, this will trigger reconnection. This is the schematics of how it happens. And this Ohm's law, it captures this phenomena where the eta you can see on the RHS. So this is the resistivity that triggers reconnection. Now in this process, the magnetic energy gets converted to plasma kinetic and thermal energy. And in certain extreme environment where the magnetic field lines are very strong in magnitude, like the magnetars, pulsars, and black holes, we can find the Alfvén speed, which can become comparable to the speed of light. In those regions, the relativistic magnetic reconnection becomes important. So motivation, in relativistic magnetic reconnection, the high sigma regime remains largely unexplored. The sigma is the magnetization parameter, which is the ratio of magnetic energy density to the rest energy density of plasma, and the mechanisms underlying the energy conversion in these extreme environments are not yet fully understood. The certain global general relativistic MHD simulations have shown that magnetic islands formed in reconnection can explain the black hole flares, and the details of the energy transfer remains unclear, where most ohmic dissipation studies are based on non-relativistic plasma. So I have referred that in the end. So the MHD is crucial for collisional plasmas and large-scale systems where kinetic simulations are infeasible due to extreme scale separations. Below here are some graphics of magnetar, pulsar. The last one is of black hole. So we'll first understand a basic Sweet-Parker reconnection model. So it is a steady-state reconnection model which helps in understanding resistive MHD. Okay. So here we have antiparallel field lines, and this is a thin current sheet form of sheet width 2D and length 2L. So this green indicates the flow of plasma. So the plasma, along with the magnetic field lines, comes into the diffusion region where the field lines get reconnected, and along with plasma, it is ejected out along the sheet, or is thrown out. So first we'll look into the Ohm's law. So this Ohm's law at point O, where the magnetic field is negligible, we have E as only eta j, and at the region P, where resistivity is negligible, we have Vi. Along with the Ampere's law, we obtain an expression for D, the sheet width. Now, if we substitute this D in the mass conservation equation, we get a relation of Vi by Va, which is nothing but the reconnection rate. It signifies how the reconnection takes place, or how fast, and it is inversely proportional to S, which is the Lindquist number, which is nothing but inversely proportional to the resistivity. The stronger the resistivity we have, the more stronger reconnection we can find. That is the steady-state equation of motion on the top. Okay. There, the J cross B, the Lorentz force term, it takes the plasma from point O to point L to the top. And in those regions, the pressure gradient can be taken as negligible. And we'll take expression from Gauss' law. And what we obtained is that the VO, the outflow velocity, is nearly equivalent to the alpha velocity. And if we substitute this here, we get the reconnection rate scaling of R proportional to S to the power minus half. So S is the Lindquist number. So the Sweet-Parker model gives us a useful scaling for reconnection rate. We do a relativistic resistive MHD simulation. Use black hole accretion code, the VAC code, and initialize with a Harris sheet. The Harris sheet has a tan hyperbolic functional form, and we had perturbation for reconnection. And the perturbation has a Gaussian form. Our plasma has a beta parameter of 0.2, which is the ratio of the thermal energy to the magnetic energy. So this is the coordinate space, and this B is the tan hyperbolic function. And you can see there are antiparallel field lines present near the origin, because of which we get a current density, J, along the Z direction. And this is present throughout the XY plane, and hence we obtain a current sheet. Now we'll look into a simulation. Now this is on the XY plane, and that red one is the current sheet along Z direction. And this green arrow indicates the flow direction of the plasma. What we'll do is we plot a reconnection rate, how it varies with time. And this is for a particular Lindquist number, 4100. So you see, as the reconnection is triggered at the center point origin, now the thinning of current sheet takes place. So thinning and elongation takes place. At that time, a magnetic island is formed on top and bottom. This starts flowing outside of the simulation domain, and there is a blue line which indicated the sheet length when it reaches 0.4 unit. Now you can see we get a beautiful graph of the reconnection rate. What you see is that the reconnection rate increases and keeps on increasing up to a peak height, after which it starts decreasing because of the formation of the magnetic island, which slows down the reconnection process. And later on, when that island moves out of the simulation domain, the reconnection rate again peaks out. And that particular characteristic time is indicated by that star, okay, at which time we calculate the reconnection rate. Now, similar simulations were done for different Lindquist number. So to recap, again, if we increase the Lindquist number, it is just reducing the resistivity. So what we see is that with increase in resistivity, the reconnection rate increases. And if we plot the reconnection rate with Lindquist number, we obtain a scaling of R proportional to s to the power minus 0.45. In this way, verify the Sweet-Parker scaling in the relativistic regime. Now we'll look into the energy conversion process that takes place in this. For that, we take the Faraday's law, we do a dot product of B, and substitute this curl of B with Ampere's law. We obtain the energy conservation equation, which is this one. So as you can see, there is a electromagnetic energy density term, derivative with T. There is a S term, which is the Poynting flux responsible for transferring energy. And there is a minus J dot E term, which acts as a source term. So what it shows that the J dot E term, it measures how much energy is converted from magnetic energy to the plasma. And if it is negative, then the plasma gives back energy to the electromagnetic field. We do temporal analysis of J dot E, like how it varies with time. So for that, we take the relativistic Ohm's law, we cross it with V 2 times, and we get the J dot E per V. In our simulation, there is no electric field component parallel to the velocity field, hence we obtained this expression. And now you can see there are two terms here. The first one is the convective electric field, and the second one is like a resistive electric field. If you see the below plot, you can see that initially, most of the energy conversion process is taken up by the resistive electric field, and later on, it is taken up by convective electric field. But later on, I mean like when the plasma actually starts moving, or the magnetic island actually starts moving towards the edge of the domain. Okay. And interestingly, you can also see that the pink one is the reconnection rate graph that we obtained earlier. Now, when the reconnection rate reaches to its maximum peak, we see that we get equal contribution from both convective electric field and resistive electric field. And finally, that green line, which shows the total energy conversion, and we see it keeps on increasing and increasing until and unless the magnetic island goes out of the domain, which also signifies that maximum energy conversion was taking place somewhere close to the magnetic island. For that, we did a spatial analysis of J dot A, like how it varies with space. Now, in the first left-hand side figure, you can see there is a red region and the blue region. In the red region is where the electromagnetic fields are giving their energy to the plasma or energizing them, and the blue region is where the plasma is giving back energy to the magnetic field lines. And if we separate it out and see that the convective electric field is both positive and negative, that is, it gives energy to the plasma and takes away from them, and it is stronger near the sheet edge and the magnetic island. So this is the magnetic island, this is the sheet edge. And the resistive electric field, it is only responsible for giving energy to the plasma, and it is stronger inside the current sheet here and near the separatrix region of the plasmoid. So these are the regions where actually most of the energy conversion takes place, and that is why when they move out of the simulation domain, our energy conversion graph was dropping. To understand the inflow and outflow dynamics of the plasma, we do a sigma scaling. So this sigma is the magnetization parameter. So it shows the increase in magnetic energy from left to right. Okay. So what we see is that Lutikov predicted the inflow scaling. So beta n is inflow scaling of beta n proportional to sigma by s to the power 0.5. By doing so, he assumed most of the magnetic energy gets converted to the kinetic energy. So the green line is the predicted scaling, and the red line is what we get in our simulation. Similarly, Lubarsky predicted outflow scaling of Ui proportional to sigma to the power 0.5, and he assumed incompressibility and hot outflow. Again, the green line is the predicted one, and red line is what we obtained. So what we obtained is a weaker scaling than that was predicted. So we investigated why that was happening. So for that, we take the compressibility factor. So we have the mass conservation equation, and we add compressibility factor to it, which is the ratio of the inflow mass to the outflow mass. So this is the magnetic island, and this is the domain we choose, which is free from the island, to look into the inflow mass and the outflow mass. By introducing this alpha factor, and for our simulation, our rho in is equal to 1 throughout the simulation. Delta by L is nearly equal to B out by B in, which is constant. And the beta out, which is the outflow velocity, it is the independent of sigma. So it does not vary with magnetization. So what we obtained is a scaling of alpha proportional to beta in by rho out. And by substituting the simulation sigmas of 0.1 and 0.52 for beta in and rho out respectively, we obtained a scaling of 0.42. To verify this one, we also calculated the alpha scaling from our simulation result, and we obtained 0.47, and the both of them are pretty close to each other, which signifies that okay. So which signifies that compressibility factor should be taken into account. Then we do a energy partition where we look into like how the energy is partitioned in between magnetic energy and thermal energy and kinetic energy. So the inflow, the solid lines are the inflow. It shows that the magnetic energy is dominating and it keeps on increasing with sigma as expected. And secondly, the thermal energy has significant presence here. The outflow, whereas the outflow is completely dominated by thermal energy, close to 90%, which was also found by other people in their PIC simulation. So the addition of guide field BZ, we also added guide field, and it does not have significant impact on the energy composition. That is, the graph remains same for the outflow. And the reconnection rate decrease with increase in guide field strength, which was also expected. So the compressibility and thermal effects in the outflow and inflow are important for reconnection dynamics. So in conclusion, magnetic reconnection is a fundamental plasma process that powers dynamic phenomena across a wide range of environments, from solar flares and auroras to laboratory plasma and accretion disks. This work is crucial for developing a comprehensive understanding of energy conversion mechanism in reconnection events occurring near the event horizon. Our study gives a scaling for compressibility and thermal effects in the collisional regime, which significantly influence the reconnection dynamics. You can find more about this work in this archive paper. These are my references, and thank you all for your attention.
Yeah, any questions from the audience? Yeah, I think there's a question.
In the first slide, you said that the before reconnecting happen, the field lines break. The field line breaks before reconnection happen.
Yes, yes.
So why does it break?
What is the?
Why does it break?
Oh, why does it break? Now it breaks because of the presence of resistivity. The resistivity allows the field lines to fuse through the plasma. Like they can leave one fluid element, fluid plasma, and can move to another one. So,
like resistivity between, like I didn't understand what that is.
Resistivity is the eta term. Resistivity, like it comes from the Ohm's law. So if you have resistivity, like suppose we have a plasma sheet sitting like that way, in some small region there can be resistivity in space plasma. So that resistivity, what it does is it forces the field lines to break, rejoin, and throughout the plasma here and there. So those are the points of reconnection that occurs.
Just to think, what is the source of that resistivity?
What is the source of resistivity? Okay. Like it is.
Why does that resistivity arise? I mean, what is?
Okay. So it is when still now we are trying to understand reconnection more about like why that location reconnection is happening, the localization mechanisms and all. And I don't have a clear answer like what physically goes into it, like how that resistivity zone is selected. It is still an area of discussion. Yeah.
Thank you.
Thank you.
Hi, Harier, nice talk. My question is that you are using Sweet-Parker model in your simulation to study magnetic reconnection.
I'm verifying the Sweet-Parker reconnection, which is mostly considering non-relativistic equations, as you can see the alpha and speed and all. So I'm doing a relativistic simulation, but in this simulation, the results that we obtain, it matches close to the Sweet-Parker model.
Okay, so there is another prominent reconnection model by PSSI model.
Yes.
So PSSI model प्रेडिक्ट करता है कि रिकनेक्शन रेट जो है वो उसमें पेशेक मॉडल में ज़्यादा होती है. सो कैन वी वेरीफाई और वे कैन वी यूज पेशेक मॉडल टू सिमुलेट reconnection in
Okay. Yeah, it's a very good question. Like, yeah, there is a Peschek type reconnection which gives a more faster reconnection. But if you look into carefully, the Peschek type reconnection has what you say shock waves present in them. So there is shock waves present along the sheet edge that helps to localize the reconnection into a smaller region, and that enhances faster reconnection. In our simulation, we don't obtain such shock waves. So we cannot verify Peschek scale, but if your simulation obtain some shock waves kind of thing near the reconnection region or magnetic island, then yeah, there you can go and verify the Peschek type reconnection.
Thank you.
Yeah.
One more question from the audience, anybody?
What is the maximum Lundquist number you can do in your simulation?
Maximum Lindquist number, so we go close to 10,000, but to going above that, we need more simulation power. Actually, we are working on 4096, but yeah, we can go to like 15,000 something if you have 8K or 16K resolution.
Because you will still not be seeing the fast reconnection unless you go to really high.
Yes, yeah, that's the computationally restricting us to work in this regime.
Good talk.
Thank you.
So I think no more questions, and you are, I think, running late for lunch, and Nishant is going to be really upset. So this, one more round of applause. And so this, so thank you, Harin Pradhan. So we now, I think I hand it over to the session. Session comes to a close. Actually, I hand it over to the organizers. Thank you.
Now this is the end of this fundamental session. I invite our convener, Dr. Nishant Sisse, to present a memento to our first session chair, Professor Ramesh Narayan. I request to all talk presenter of this session to please come on the stage for the session group photo. Deepak Raj Purohit, Arindu, Libin and Harihar, please come on the stage. Thank you, all of you. Now we have a break for lunch, but we have short time, so lunch will be around 30 to 40 minutes only. Thank you.